Now let us come to the fourth and the most important and unique polymerization technique, which is emulsion polymerization. Now, emulsion polymerization is a unique technique or process that involves emulsification of hydrophobic monomers. Now, like suspension polymerization, here also hydrophobic monomers are used, and the nature of the emulsion could be oil in water, that is your hydrophobic monomer dispersed in water, or any polar liquid, mostly water is used, so that way it is called oil in water emulsion, which is the general or the normal emulsion. And in that case the reaction is initiated with either a water soluble initiator, means medium soluble initiator like potassium persulfate, so that way it is different from the suspension polymerization where we have used monomer soluble or oil soluble initiator. So in most of the cases in oil in water or the normal emulsion, the water soluble initiator like potassium persulfate is used, or in few cases an oil soluble initiator can be used, but this is very rare, and in that case AIBN can be used, which is water insoluble and soluble in oil or organic solvent. And in all this, these are being stabilized in an emulsion with the help of either ionic or non-ionic stabilizers, and these non-ionic stabilizers, they are often called protective colloids, and these are basically active or aids the dispersion of this hydrophobic monomer in the aqueous medium. Now, in emulsion polymerization, of course, we have to use these vinyl monomers. That is, they are having this CH2 double bond CH, this part in their structure, and they would undergo the free radical polymerization with the help of water insoluble initiator. And what we see, this emulsion polymerization technique means the polymers formed through emulsion polymerization, they find a wide range of applications such as synthetic rubbers. Most of the synthetic rubbers or important synthetic rubbers, they are being synthesized using this emulsion polymerization technique. Then several thermoplastics and also the polymers which are formed finally in the form of or obtained in the form of polymer latex, just like in suspension polymerization we described that if you can resist the precipitation in suspension, you can also obtain the polymer latex. So here also you can obtain finally the polymer in the form of the latex form, because it is also a heterogeneous system. So that way that polymer latex or that emulsion can directly be used as a coating application in adhesive application, or it can also be used as binders, rheological modifiers, and pigmented plastics, means whereby the pigment can be dispersed within the plastics itself in this your dispersion mode or emulsion mode, etc. So that way pigment modified or pigmented plastics, that way it can be obtained from this technique. Now, how this emulsion polymerization is very different from bulk suspension or even solution and even suspension. Suspension is also a heterogeneous technique, but this emulsion is widely different from all these three previous techniques, because this polymerization is rather a complex process, and it constitutes of particle nucleation, their growth, stabilization, and finally dissipation of the reaction to form finally this polymer latex particles. And uh, and this this entire process is associated with several colloidal phenomena. Now, aside from other polymerization techniques, this technique further affords an increasing molecular weight of the formed polymer latex through decreasing polymerization rate by either decreasing initiator concentration or lowering the reaction temperature. So here you can see the molecular weight increment in this emulsion polymerization technique. It is achieved by decreasing the polymerization rate, and that decrement in the polymerization rate can be achieved either by decreasing the initiator concentration, because we know that once you decrease the initiator concentration, then what happens, the molecular, I mean your the rate of polymerization is decreased, because we know that rp is proportional to your concentration I to the power half, though, but still it is directly proportional. But here, because of this so many colloidal phenomenon going on in this technique, so we have if you want to have an increasing molecular weight of the polymer, so there you need to decrease the rate of polymerization, and for that the initiator concentration is decreased or the temperature can be decreased, means the polymerization should be carried out at lower temperature, and that way we have the provision of low temperature emulsion polymerization. So low temperature emulsion polymerization or a very low concentration of initiator actually favors the high molecular weight formation in this technique through a decreasing rate of polymerization. Now, systems of emulsion polymerization involve conventional emulsion polymerization, that what we are referring so far, that is oil in water system. So this is what we call it as a normal or conventional emulsion polymerization, in which a hydrophobic monomer is emulsified in water and polymerization is initiated with water soluble initiator. So this is the constitution of a conventional emulsion polymerization system. Then we can have the inverse emulsion polymerization system, means just the reverse, where we have where the organic solvents of low polarity as paraffin or xylene is used as the polymerization media, and hydrophilic monomers are emulsified within it. So here you have just inversion of the role of the components, that is your hydrophilic monomers are emulsified within a non-hydrophilic dispersion medium, and the initiation proceeds with the aid of hydrophobic initiator. So here the initiator would be hydrophobic, means in normal emulsion or conventional emulsion you have hydrophobic monomer dispersed in water and water soluble initiator is used, whereas in inverse emulsion you have hydrophilic monomer dispersed in hydrophobic media and you have oil soluble initiator being used to initiate the polymerization. So these are actually referred as oil in water, that is your conventional polymerization, and water in oil, that is your inverse emulsion polymerization. Now there could be other variety like mini emulsion polymerization, which involves systems with monomer droplets in water with much smaller droplets than the emulsion polymerizations. Mean whatever be the size of the droplets of monomer in conventional emulsion polymerization, in mini emulsion polymerization the droplet size is even lower than that, and that way it is called the mini emulsion polymerization, and the droplet size is between 50 to 1000 nanometer in mini emulsion polymerization, and for that the surfactant concentration should be used much higher than the that what is being used in case of emulsion polymerization, and that surfactant is what we call it as a stabilizer or emulsifier that is being used in case of the emulsion polymerization. So its concentration should be higher in case of mini emulsion polymerization, and also there could be micro emulsion polymerization, and micro emulsion polymerization we have very much smaller monomer droplets much smaller than the mini emulsion process, that is where the droplet size was 50 to 1000 nanometer, and in micro emulsion polymerization the size should be within 10 to 100 nanometers. So accordingly we have to use much higher surfactant concentration, and there actually we get even finer dispersion of these monomer droplets within the water medium. Now we were mentioning this surfactant or your emulsifier, or what we call it as a stabilizer for emulsion. Now these has the major role in defining whether the process is a conventional emulsion, or it is a mini emulsion, or it is a micro emulsion. Its concentration actually plays the role where you are using higher concentration of the surfactant or stabilizer, that would help the dispersion of the monomer in a much finer size, whereas when the concentration is less, then the dispersion size or the size of the dispersed monomer, that is also a little bit higher. Now, this surfactant or emulsifier or stabilizer, these molecules are basically a specially designed molecules which has this hydrophobic, tail and a polar head. So this, if you call it as a head, it is polar in nature, and this tail, it is your non-polar or hydrophobic in nature. Right. So because of the existence of simultaneously this hydrophobic chain as a tail and a small hydrophilic part or polar part as a head, so this kind of molecules in one hand, they can bind with the dispersion medium, that is water, their polar head, and this non-polar tail, they can bind with the hydrophobic monomer, and that way they can bring this hydrophobic monomer very close to the water by reducing the surface tension, and aids the dispersion of the monomer in much finer size in an emulsion than what we had obtained, or what we get in case of suspension polymerization. So that way the uh, dispersed size in emulsion polymerization is much finer as compared to the suspension polymerization. And within emulsion we have the further refined size in terms of conventional polymerization, then further lowering in size in case of mini emulsion polymerization, and even further lowering in size in case of micro emulsion polymerization. Now the this your in your this surfactant or emulsifier, which has this kind of your structure, that is a hydrophilic head and a hydrophobic tail. So they actually maintains the hydrophilic and lyophilic balance in the medium, and for that the surface tension of the medium is reduced, as I mentioned, and we have a very fine dispersion of the monomers within the dispersion medium. Now these your surfactant molecules, as mentioned, that it could be ionic type or non-ionic type. So when it is ionic, again it could be cationic or it could be anionic. That is, cationic means bearing the positive charge. For example, cetyl trimethyl ammonium bromide, CTAB, or it could be anionic like sodium lauryl sulfate. So it bears a negative charge. So that way we have a cationic surfactant and we have an anionic surfactant. And if it is non-ionic, then it does not bear any charge. And the non-ionic surfactant are mostly referred as the protective colloids. And protective colloids means they actually stabilizes the in emulsion polymerization, they actually stabilizes the final stage product more effectively. That is, the when the polymerization is over and we have the dispersion of the polymer latex that is being stabilized by this non-ionic surfactant. So that way, in the component you have to use an ionic surfactant for the polymerization stage, and a non-ionic surfactant to stabilize the product. So a combination of an ionic surfactant, which is mostly an anionic one in case of conventional polymerization, an anionic surfactant and a non-ionic surfactant, a combination of these two uh, must be used in case of emulsion polymerization in order to have a final very stable dispersion of the polymer particles, or what we call it as a latex. Now, in emulsion polymerization, when this surfactant is used above a certain concentration of the surfactant, they solubilizes in some aggregated form, which is called micelle. And this aggregation of surfactant, that creates a special geometrical shape. It could be spherical like this, spherical micelle what we call it, or it could be your rod shaped like this. And when these surfactant molecules are associated, their association becomes in this fashion, that the polar heads, they are directed towards the hydrophilic your solvent, or hydrophilic dispersion medium like water, and the nonpolar tails, these parts are aggregated inside that association. So we have in the outer surface the polar hydrophilic part, and in the inner portion we have the nonpolar hydrophobic part, and that way the association takes place above a certain concentration of the surfactant, and that concentration is called CMC, or critical micelle concentration. Means the surfactant above a certain concentration, they form solubilized aggregated structure called micelles, and the concentration above which the micelle formation takes place is known as the critical micelle concentration. Now, this your system, the dispersion medium, as I mentioned, is water. The monomer is emulsified by the surface active agents, that is surfactants, and when the surfactant concentration exceeds the critical micelle concentration, it aggregates in the form of spherical micelles, or it could be, say, rod shaped micelles, whereby we have in the outer side these polar heads, and in the inner side these non-polar tail. So that way it can also give you rod like association, or it could be a lamellar association like this, a lamellar association. So it is not only the spherical association, it could be rod shaped, or it could be lamellar association. It depends on the surfactant molecules which is being used. So that way the micelles are being formed, so the surface tension at the surface decrease, and as a result the hydrophobic monomers, they start to enter into the vicinity of this micelle, and these micelles then act as the locus of the polymerization. So here you see that in this system, which is in an emulsion polymerization system, so far we have discussed the role of, the monomer, the dispersion medium, and an emulsifier, that is your what we are referring as the surfactant, and the presence of initiator. So when these systems are present, then these initiator, these surfactant molecules above their micellar concentration, they will start to form these micelles, and also the other surfactant molecules which are not exactly the part of these micelles, they will help to form the monomer droplets, these finer monomer droplets. So that way we have water soluble initiator which is soluble in water, then micelles formed by the surfactants and the monomer droplets, which is formed by the monomer stabilized with the help of the surfactant molecules. Now, in these micelles, as I mentioned, that we have outside the polar part and inside the non-polar part, means hydrophobic part, and monomer by nature it is hydrophobic. Then what happens, some of the monomers which are not yet the part of the monomer droplet, so some of the monomers, they will take entry inside these micelles, right, and they will swell the micelles a bit, and that way, in the beginning when the polymerization has not initiated, then we have the monomer droplets stabilized by the surfactant. Then we have micelles, which some of the micelles which contains these monomers, and that way monomer solen micelles. So these are the two your draw I mean what we call it as a droplets, you can say, because monomer is liquid, so that way it's a droplet. And we have these your some of these monomers entered within this micelle, so some droplet swollen your micelles, so these are present in the beginning. Now these micelles, it contains about 50 to 150 surfactant molecules together, and the typical dimensions of these micelles are within 2 to 10 nanometer. And once some monomers are being diffused inside, forming this monomer swollen micelle, then the size is increased a bit. So the micelle, which the size is originally around 2 to 10 nanometer, and after diffusion of the monomers inside these micelles, its size would increase a bit from that, and the monomer droplets, they shall be much bigger in size, right? The monomer droplets are much bigger in size as compared to these micelles. And here you can see the picture. So you have these large monomer droplets, and here you can see it is stabilized by these surfactant molecules. And here you can see that the surfactant molecules are these black your spheres. These are the polar heads, and these are the non-polar tails, and these are what we call it as a micelle. So these micelles, they also contains some monomer inside. So we have these your monomer solen micelles. So you can means if you compare the size, you can see the monomer droplet is of much bigger size as compared to the monomer solen micelles, and these are the other dispersed surfactant molecules present in the dispersion medium or water. And we also have the water soluble initiator molecules present in this water. Now, these initiators, as we have the free radical polymerization to take place, then we would take the free radical initiators, and typical water soluble initiator is potassium persulfate, ammonium persulfate, and we also use a partially water soluble peroxides like tert-butyl hydroperoxide, succinic acid peroxides, and some azo compounds as initiator. Or redox initiators can be used like cumyl hydroperoxide and ferrous ion combination, or ferrous ion and hydrogen peroxide combination, or ferrous sulfite or bisulfite combination with your peroxides. So that way, these sort of redox initiators are also used in case of your polymerization. Now, surfactant, as I mentioned, that surfactant molecules, these have a non-polar or hydrophobic tail, followed by a hydrophilic head. So these your surfactants, they, because of their unique structure, they actually help to decrease the interfacial tension or surface tension between the hydrophilic dispersion medium, that is water, and the hydrophobic monomer or the water insoluble phase. And also they help to stabilize the polymer particles which is formed, which is referred as the latex, and they generate micelles where the polymerization takes place, and that way the particle nucleation occurs. Now surfactants increase particle number and decrease the particle size, right? Means in suspension polymerization we did not mention the use of any surfactant. For that the particle size was 0.0012 to about 1 centimeter, but here the particle size is much less than that because of the presence of this surfactant, and this surfactant, as it reduces the surface tension between this hydrophobic and hydrophilic part, so that way it decreases the particle size and increases the particle number. So this is a unique behavior of the surfactant that we can see in emulsion polymerization. And as it was mentioned that you can have these ionic surfactants like anionic surfactant such as fatty acid soaps like sodium or potassium stearate or sodium laurate, sodium palmitate, that is your sodium lauryl sulfate, uh, your and sulfonates like that. Or you can have your cationic surfactant like your cetyl trimethyl ammonium bromide or CTAB or dodecyl ammonium chloride. So these are your cationic surfactant, means which bears the cationic charge, and your anionic surfactant, it bears your negative charge. And another variety is a non-ionic surfactant which does not bear a charge, and for example polyethylene oxide, polyvinyl alcohol, hydroxyethyl cellulose. So these acts as a non-ionic surfactant. And in oil in water emulsion, or what we call it as a conventional emulsion, we use these anionic surfactant for stabilizing the micelle, or rather for the formation of the micelle where the polymerization occurs or the polymerization takes place, and a non-ionic surfactant as well, which acts as a protective colloid of your finally formed polymer particles or latex. So that way we need a combination of these anionic and non-ionic surfactants for a perfect oil in water emulsion polymerization. For ionic surfactants, micelle formed only at temperatures above the Kraft point. Now this Kraft point is that temperature above which the micelle is being formed from the surfactants. So these ionic surfactant, specifically these anionic surfactant, they forms the micelle above the Kraft's temperature. And also you need that concentration wise, you have to exceed that critical micelle concentration for this surfactant. So that way you can say that the Kraft temperature is very close to that of the critical micelle concentration of a anionic or ionic surfactant. Whereas for a non-ionic surfactant, also we have the micelle formation, but that micelle formation occurs only the temperature below its cloud point. Cloud point means where the surfactant, means the temperature above which the surfactant becomes insoluble, right? The surfactant, the non-ionic surfactant becomes insoluble. So remember, for ionic surfactant, we have Kraft, we have Kraft temperature, means that Kraft temperature means the temperature above which the micelle is being formed, right? Means temperature above which micelle is formed by the surfactant. Whereas the non-ionic surfactant, they does not have a Kraft temperature, they have a cloud point. Cloud point means the temperature above which we have this non-ionic surfactant becoming insoluble in water, and it is forming a cloud. That is why the temperature is called a cloud point. So for non-ionic surfactant, we have what? Cloud point or cloud temperature. So a polymerization, very important, an emulsion polymerization should be carried out below the cloud temperature and above the craft temperature. Very important. That is means when you are selecting surfactants, means anionic surfactant and a non-ionic surfactant for your polymerization. So you must see what is the craft temperature of the anionic surfactant, what is the cloud temperature of your non-ionic surfactant, and you must choose a temperature within these two for polymerization. And also the initiator that you will be using, what is its half-life at that temperature. So these points are to be considered before you select an emulsion polymerization system. Very, very important point to remember. That is, an emulsion polymerization should be carried out below the cloud temperature of the protective colloid or the non-ionic surfactant, and above the craft temperature of the ionic surfactant, particularly anionic surfactant. Now, regarding dispersion medium, water is used as the dispersion medium. It represents the medium of transfer of monomer from droplets to particles, and as a solvent for emulsifier, initiator, and other ingredients. So this water is used as a dispersion medium. It helps to disperse these monomer droplets, the micelles. Uh, it solubilizes the initiator. It solubilizes a part of the emulsifier and other ingredients that are being used. So that way, the dispersion medium, or that is water, in conventional polymerization plays its role. And during polymerization, it also plays a very important role. That is, the polymerization occurs in this micelle. Means you have this micelle where the polymerization is taking place, means micelle acting as the locus, and you have these monomer droplets. So during polymerization, the monomers, they I mean they get transferred from these monomer droplets to this your locus of polymerization, that is within the micelle, through this dispersion medium, that is water. So it also acts the transfer medium for monomer from the monomer droplet to the locus of polymerization, that is the monomer solid micelle. So it acts as a transfer medium, and this is a special role being played by water in conventional polymerization, emulsion polymerization technique. Now, regarding monomer, the monomer should be hydrophobic as already mentioned, and they should be your vinyl derivatives, because you are adopting a free radical polymerization. So monomers such as your acrylic acid, butadiene, styrene, acrylonitrile, acrylate ester, methacrylate ester, etc. Can be used. Now, monomers, we mentioned that the monomers should be hydrophobic in emulsion polymerization technique. Now, if you use monomer like acrylamide, then you have to go for inverse polymerization, because acrylamide is water soluble. But apart from acrylamide, these acrylic, butadiene, styrene, etc., these are water insoluble, and we can go for this conventional emulsion polymerization technique. Now, the solubility, I was mentioning the solubility of the monomers. Now, when you are using hydrophobic monomers, it means that their water solubility is very, very poor. Now, how much it is soluble in water? Maybe less than 1%, less than 1% soluble, or it may be soluble to the extent of 2 to 3%. So that actually creates a lot of difference during the initiation of the polymerization. Now, if you have about less than 1% water solubility of the monomer, then the initiation process takes place in the monomer solid micelle. Whereas if you have 2 to 3% solubility of the monomer in water, then the initiation can take place in the water, means initiation of polymerization. And why I am saying this, you have the initiator molecules soluble in water, so they will decompose in water and produce the initiator radicals. Now if they find enough monomer available in the water in terms of this 2 to 3% solubility, then they can start or they can initiate the polymerization in the water itself, and they can give you some extent of growth in the water medium itself, and then they afterwards, as they will get more hydrophobic, then they will start to migrate within the your monomer solid micelles. Now but if the after this dissociation of the initiator molecules in water, they do not find enough monomers in the water because of the solubility much lower than 1% even, then they will migrate straight within the micelle where the monomers are present. So that way the initiation would take place in the micelle itself. So the water solubility, the extent of water solubility I would mention about of these hydrophobic monomers, that actually controls the locus of initiation process in the emulsion polymerization. Now, apart from these constituents, some other essential constituents are also used, uh, and these are, say, for example, antifreeze additives. Means when we go for low temperature polymerization, in order to have higher molecular weight, uh, two ways you can have. It was mentioned that the initiator concentration should be low and that temperature of polymerization should be low. So if you opt for low temperature emulsion polymerization, then you must use antifreeze additive, just like you resist the freezing of petrols in car by using antifreeze additives. So that way you must resist the freezing of water during emulsion polymerization by using antifreeze additives, which involve inorganic electrolytes, ethylene glycol, glycerol, methanol, monoalkyl ethers of ethylene glycol, etc. And using these additives, you can do polymerization even below 0 degrees Celsius using water as the dispersion medium. Apart from this, you can use sequestering agents which used to solubilize the initiator system or to deactivate the traces of hardness elements like the presence of calcium ion, magnesium ion, etc. in water, because they can change the ionic strength, and that way they can destabilize the micelles, and action of the surfactants can be hampered. So that way sometimes EDTA, ethylene diamine tetraacetic acid, or its alkali metal salts can be used such that they can form the chelates with these calcium and magnesium ions, and they can deactivate them in from participating in the emulsion technique or intervening in this polymerization by changing the ionic strength of the medium. And apart from that, buffers are also used to stabilize the latex, particularly by resisting any change in pH during polymerization. And that way, the phosphate or citrate salts are used as buffers. And apart from that, if you want to control the molecular weight of the polymers formed in emulsion polymerization system, so you can also add the chain transfer agents, for example mercaptans, as additional component in emulsion polymerization.